Okay, now we're going to go into the second part of plate tectonic theory. We're going to talk about some of the observations that led to predecessor theories that were eventually disproven. First of these is, for a long time, people noticed thick packets of shallow sediment deposits, or maybe better to think of it as thick deposits. Thick deposits of shallow sediment. The thing about these thick deposits of shallow sediment is you can't really explain them if the crust stays in the same position, because sea level does not rise and fall that much. We're talking the greatest rise and falls ranges in sea level are on the order of about 600 meters or so, maybe a little more than that, and we're seeing packets of shallow water sediment that are thousands of meters thick. So what this tells us is there has to have been vertical motion of the crust. We're just going to put this in here under hypothesis. Crust. And this will go into sort of a deeper range of hypotheses. Second big observation, this will go to our little PowerPoint, is this sort of mountain ranges close paralleling the coastline. Coastline. This is also somewhat consistent with parallel motion. And then finally, we're going to put third one here, this sort of puzzle-like fit of the continent. Presence of life on continents widely separated. We have presence of life, of fossil life, on continents that are now separated by vast oceans. So, for example, we see all these different life forms from a long time ago that clearly don't look like they can swim very well, that are present on multiple continents that are now separated by vast oceans. And so the first conclusion, so the first hypothesis for this had this sort of vertical motion of the crust as something. We definitely have evidence for this vertical motion, though we'll see exactly the limits of this in a bit. We're going to range all these in sort of a, we're going to call all these observations what we call the pre-World War II. Two observations, because what happens after World War II? Is that things start to look a little bit different. So you get this vertical, so all these, the best geologists at the time had all these observations at their disposal. We'll go over them just a little longer. And came to develop what we call the geosyncline hypothesis. Now don't think too hard about this, but this was the dominant sort of paradigm in geology at the beginning of the 20th century and up through the successive decades. And if you look at old geology textbooks, they'll describe geosyncline theory in excruciating detail. So the idea is, we knew the Earth's crust was sort of kind of floating on the asthenosphere mantle. And we know that when you have sort of a, and we also knew the Earth's crust was rigid. And so I'm just going to do a little demo here with this filing folder. So the idea of geosyncline hypothesis is that if I take a weight of some sort, let's see, must have some rock around here. Here, my phone. It's going to depress the surface of this filing folder But as it depresses the center, like if you deposit sediment in an ocean basin, the edges of that ocean basin are going sort of upwarp. And so the upwarping is how you create mountain ranges. These mountain ranges continue to erode, you get more and more stuff deposited, and the bottom of this sinks more and more, until finally you get down enough down to the deeper, hotter parts of the mantle, and you start melting some of this sediment. The sediment then somehow expands, wells up, you get more stuff, it rises. Turns out actually you do see something a little like this on Europa, but yeah. And then it all becomes more buoyant, everything sort of bulges up, and then you get this inversion. So you may have heard the legend of Atlantis. This is kind of how Atlantis happened. But my favorite legend is not the legend of Atlantis, but the legend of Lemuria. Yes. There are lemurs on Madagascar. You've probably seen some cute Disney Pixar movies about this. And there are fossil lemurs on South India and Sri Lanka. And we know there are some large plateaus in the Indian Ocean. And so the hypothesis went that, with this geosyncline theory, that there had been a giant plateau in the middle of the ocean that was kind of this weird utopian paradise. There's even a fellowship up out near Ramona dedicated to this lost land. And that this plateau collapsed and it was sort of a Atlantis of the Indian Ocean, sort of a paradise lost. Yeah, this is kind of awesome and not actually how it went. You can also see this was connected to Western Australia. And yeah, there are some lava flows in South India, Madagascar, and on some of these plateaus in the Indian Ocean and Western Australia that look very similar to each other. So it's not completely wonky. It definitely had a lot of evidence to back it up, but as we'll see, we have a better theory that explains more of the observations now. This was your dominant hypothesis. And so we're going to put this sort of hypothesis, we're going to call it geosyncline theory. Geosyncline, I'm going to keep it fairly large, and it basically revolves around vertical motion of the crust. Now, geosyncline theory also makes a prediction. It predicts that the oldest ocean floor will be at ocean center. You'll find the oldest sea floor at the center of the ocean basin. So these two are kind of linked to each other, and we can test this at some point. Now, at the time this was created, we didn't have any way to get the age of the sea floor. But by World War II and the following decades, we got very good at getting pretty decent dates on how old stuff was on the sea floor. So we have this sort of nice linked model here. I'm going to circle all this stuff together. I'm going to show how these all go into this. And we have a nice little predictive model here. All right. So then however, there was a brave soul who took these same lines of evidence and suggested instead of vertical crustal motion, you had horizontal crustal motion. This was Alfred Wegener's continental drift hypothesis. We all know Alfred Wegener's continental drift hypothesis worked, had the same observations, noticed the same, the puzzle, also noted the puzzle-like fit of the gland masses. Here. And from all these observations, suggested that there had been at some point that the continents had moved horizontally, plowing through the oceans, and at one point they had fit together like a puzzle piece. And Alfred Wegener's continental drift hypothesis also made a prediction. It predicted that at some point in the past there was a vast landmass of all the continents together called Pangea, surrounded by a world-girding sea called Panthalassa. It was relied on horizontal movement of the continents through oceans, and it made a prediction of Panthalassa. Pangea supercontinent. And so because it predicted this, we're going to turn that into a testable hypothesis. We're going to create that as an experiment related to it. Oceans, and also I'm going to remark that the horizontal motion of the continents through the oceans was powered by tides. Tides. Okay. So now we have two competing hypotheses that both sort of are models for the Earth. One of these clearly, and so here we go. We'll use a different color pen here. We'll use the purple pen. So 1915, Alfred Wegener published the continental hypothesis in a piece called The Origins of the Continents and Oceans. He was quickly laughed out of the room. Reason being that tides are not going to be able to move continents, and it turns out basalt is actually, which the seafloor is made of, is actually pretty darn rigid. It's going to be very hard to plow through it. Not to mention, if you look at places like the Red Sea Basin, yeah, Arabia and Northeast Africa fit all right together, but there's this weird thing called the Afar Triangle that does not fit into either one of those. And so we're going to use a red point to show where it is. So this got shot down by the experts. Now, the thing about Alfred Wegener, the reason he thought this would work is he was a meteorologist. Now, a lot of people say, what kind of meteorologist? This is the question you should be asking. Alfred Wegener was a polar meteorologist. And when he did polar meteorology in that time, he went to Greenland because that was where he had polar weather. And he went there during winter because that was when the weather got extra polar. He went to Greenland 4 separate field seasons. He came back from 3 successive field seasons. Yeah, died alone, humiliated by things. However, and this is probably where I should end the lecture, but I want to give you one glimmer of hope for our hero Alfred Wegener, which is that now the leading earth science research institution in Germany is named after him. So how did he go from being the laughingstock of the earth science world to like the head name on a leading research institution of the country he came from? Tune in for the next lecture.